Hello, everybody. Welcome back. Today we're talking about linear equations versus linear inequalities. We'll be talking more about linear inequalities as we move into the optimization unit, which is this unit. When we started, we talked about equations, and they form a nice basis for solving inequalities, but they are a little bit different. Here, I give an example here. When you solve equations, we all know the rules for solving equations, right? Whenever you plug a number in for this variable x, right, the resulting equation can become true or false depending on which value you choose. For example, if I plugged in 2 times 0 plus 5, the result is not 9. And so 0 is not a solution to this equation. We don't have to just plug in numbers to figure out what these equations are and the solutions are. We've developed ways to find that value using algebra. The rules of algebra say I can add, subtract, multiply, and divide any number to both sides of this equation, as long as I do it to both sides equally. The two sides of the equation stay in balance. Right? I remember when I was in school, my teacher would always use the example of a balanced scale. That anything you do to one side, you'll have to do to the other in order for it to stay in balance. It's a pretty good analogy. So I can find the solution to this equation is x equals 2. This particular equation only has one solution. There are some equations, like the quadratic equations that we saw, which have multiple solutions. So that's a good review for us. How do these linear equations differ from linear inequalities? Because inequalities are dealing with greater thans, less thans, there are multiple solutions, or usually multiple solutions to these things, because there are lots of numbers which are greater than 9, for example. And I could plug in 2 times 10 plus 5. That would be greater than 9. So 10 is a solution to this inequality. But I could plug in lots of different numbers. 2 times 20 plus 5 is also greater than 9. So 20 is also a solution to this linear inequality in a way that we didn't see with equations. Linear equations had one and only one solution to them, whereas linear inequalities will have many. And that's because when we're talking about greater than, less than, we're really thinking about a number line. 9 lives somewhere on this number line. Without any other reference points, I can mark 9 wherever I want to. And all of the numbers to the right of 9 on the number line are greater than 9. And so we usually use something like a number line to represent this because there are an entire range of solutions here. I can't list every single one of them. I'm going to have to come up with a better way to show that. So usually I'll use something called interval notation to show that. Let me solve this inequality first before I show interval notation. We'll solve linear inequalities much the same way we'll solve linear equations. That is, because both sides are connected with a greater than, less than sign, I can treat it like an equal sign. I only have one additional special rule to go along with that, and we'll cover that in a moment. This one solves pretty much the same way as the linear equation did. 5. Now instead of a sign, I've got a greater than. This is greater than 4. Divided by 2. Divided by 2. X is greater than 2. This would be one form of the solution. You would understand what I meant if I told you all the x values which are greater than 2 are solutions to this inequality. You would understand what I meant. So this is an okay way to leave our results. There are a couple of others. I could actually draw the number line for you. And without any other reference points, I can put 2 wherever I'd like. And I can shade all the values which are greater than 2. We might call this the graphical solution. I know it seems weird to call this a graph because it's not the same kind of, this kind of graph which you're used to. But this would be a graph for one variable. When I make this kind of graph, I do have to note one thing. Am I allowed to use exactly 2 or not? It depends on the inequality sign. Inequality signs which do not have a equal to with them, these two on the left are greater than and less than signs. These two on the right are greater than or equal to, less than or equal to. Notice the line underneath that adds the or equal to the symbol. If I have a greater than or equal to, less than or equal to, I am allowed to use 2 exactly. Whereas if I don't have that symbol, I'm not allowed to use 2 exactly. So I need to make a mark on my number line which shows, am I allowed to use 2 exactly? And in this particular case, I am not. I'm going to make an open circle to show that. Sometimes when people shade, they shade kind of outside the circle, right? We know this circle represents a single point, which is impossible to see because any thickness of a point that you draw necessarily overlaps lots of numbers which are not exactly 2. This is just a representation of I'm not allowed to use exactly 2. And so normally people would highlight, they would start outside the circle, even though they know, I know, we know, that goes all the way up until 2, but doesn't touch 2. That one's kind of a weird mathematical detail. And we have to make that kind of mark. And I used to get students which asked me, well, professor, if I want all the numbers greater than 2, why don't I start at 3? Right? That's a number greater than, and put a closed circle, which is what I would show if it was a greater than or equal to, less than or equal to. Why don't I put a closed mark at the next number and then shade from there? And because I've drawn both of these next to each other, you can probably see why. If I start at 3, then I've left out all the numbers in between 2 and 3. So I can't start at 3, right? I'd actually leave out all of the numbers between 2 and 3, which should be shaded. And I think that you would see that no matter where I started, I could repeat the same argument, right? I could start at 2.1 and shade, but we'd have the same argument. The argument would be all the numbers between 2 and 2.1 would be left out. We could do 2.01, 2.001, etc. There's no value that is greater than 2 that we could not have that same argument. No matter how close to 2 I went, I would always be able to argue you're leaving something out. And so I have to use 2 exactly, even though I can't actually use 2 exactly. It's kind of weird. And I have to mark 2 because that's the boundary. And I have to say, well, this boundary is an open boundary. So I use an open circle because I have a less than or greater than, not a less than or equal to, or greater than or equal. So it's a little weird, but we have to use that sort of open boundary mark. And we call that the graphical solution. This one would be called the inequality solution. Unsurprisingly, because it contains an inequality symbol. This one is called the graphical solution. Some people are not used to seeing graphs with a number line, but that is a graphical solution. And then one more, the interval notation solution. This one kind of cribs off of the graph solution. It says, you know what? I want to highlight a chunk of this number line. I'm just going to tell you the beginning point, the left side of the shading, and the ending point, the right side of the shading. And then you're going to shade all the numbers in between. So because the first number on the left that I shade is 2, and the last one, oh wait, there's not a last on the right. It goes that way forever. So I need a special mark which shows it goes to the right forever, and there's not a place where I stop. And that's where the infinity symbols come in. Infinity and negative infinity are not numbers I can put on the number line, at least in this class. They're more like destinations, or they're not destinations, they're journeys, right? They go forever. And so if I put comma infinity, that means I never stop. I go that way forever. So this is close to the interval notation. The only thing I have left to do is just like on the graph when I had to worry about open circle, closed circle, open circle, closed. I have to do the same thing with interval notation. Only I'm not going to make an open circle, closed circle. The mark I make in interval notation is round parentheses, or just parentheses. That would represent an open circle. On the left side, infinity always gets open, always gets parentheses. On the right side, if I needed a quote unquote closed circle in parentheses, the symbol would be square brackets. Square bracket left side, square bracket right side. So this would be called the interval notation solution. Interval notation. I guess I'll write out fully interval notation, since this is the first time we've seen it. Interval notation. It is an entire chunk of the number line, all shaded at once. So 3 forms of the solution. Right? You can see that inequality form and the interval notation form are actually pretty easy to write. They are pretty small. They're contained. We don't always have the space on our page to draw a graph, but My Open Math does have questions which will ask you to graph your solutions as well. And we should be flexible enough to see, read, and write solutions on all 3 forms. The reason we have these different forms is that we'll use them in different contexts. For example, towards the end of this video, we'll see that for some kinds of inequalities, graph will be how we have to show our answers. We don't really have the ability to write them any other way. That's linear inequalities. They solve much the same way as linear equations, with one special exception, and that's the next example. And scroll up past it. There we go. I was going to write out the rules, but now that I'm recording, I feel like most people would be okay with the rules of equations. When we have negative numbers inside of an inequality, things get a little bit hairy. I'll actually use the space that I was going to write the rules to demonstrate my point. When it comes to negative numbers, on a number line, I'll mark 0, show you where it is. The positive numbers go this way, 2, 3. The negative numbers go the other way. Notice how the positive numbers are greater when they go left to right. That is, on the number line, everything to the right is greater than. So, for example, 1 is less than 3 because it appears on the left side of 3. But the negative numbers are exactly the other way around. Negative 3 is less than negative 1 because it appears on the left side, negative. And so the order for the negative numbers seems back from the positive numbers. And because the order feels backwards, we're going to have to take that into consideration whenever we solve our inequalities. Not always, right? Because no matter where I started on this number line, if, for example, if I have two numbers which are this far apart, if I added 1 to both sides of the inequality, quote unquote, do you see how they would both move in the same direction? And so they would never crisscross. That is, my inequality sign would never be different. And so adding any number, even if it was a negative number, right? Imagine starting at the blue and going back to the red. That would be adding -1 or subtracting 1. If I'm adding or subtracting, right, they wouldn't crisscross over each other, right? So I don't need to change my inequality symbol. I don't need to worry about it. As long as I'm adding or subtracting the same number, positive or negative, nothing feels different. Compare and contrast that to how multiplication works. For example, if I started with 1, 3, now let me multiply times -1. You can already see what's happening here. If I multiply 1 times -1, I get -1. If I multiply 3 times -1, I get -3. Do you notice how when I multiplied by a negative number, the dot which was on the left became the dot on the right, and the dot which was on the right became the dot on the left? And so what this means is that I have to change from a greater than to a less than when I do that. I know I used less than symbols for both, but if you notice, what I can do is I can rewrite the same thing. And when I flip the numbers around, I flip the inequality sign as well. And we know that in the equal sign, it doesn't matter. And my joke is that the equal sign looks the same no matter if you flip it around an equal sign, it still looks like an equal sign. Joke. But I can change the size as long as the big side of the sign points to the same number. You see how in this case, the big side of the sign points to -1. No matter which side I write it on, the big side of the sign points towards -1. And so when I did this multiply by -1 operation, I had to change from a less than to a greater than. And that encompasses the idea that when I choose to go to the negative side of the number line, I flipped everything around by multiplying by a negative number. Well, it changes the idea of left side, right side, which is greater than, less. So multiplying by a negative number or dividing by a negative number causes this problem. Move this down a little bit. Multiplying by a negative number changes my inequality symbol. And note, when I'm the one that chooses to do this, this is when I have to change the sign. If the negative number is already present in the inequality, I'm not worried about it because I didn't put it there, right? Whoever put together the inequality told you which direction the inequality sign should point when they put together the inequality. It's only when you change it by multiplying by a negative number or dividing by a negative number. It's only when you change it, you need to keep track of the symbol, which changes as well. So adding and subtracting doesn't have this problem. We saw that earlier. Right? We can shift both of the dots left and right, and the one on the left would stay the one on the left. The one on the right would stay the one on the right. Only multiplication and division has this problem. Let's see how that looks, because there's a couple of different ways that I can account for that. Right, so method one is I have to learn the new rule, and I'm going to apply that new rule whenever I see it. And so in this case, I'm going to apply the rule when I come across it. So let me start. I'm going to get the x's by themselves by subtracting 5 from both sides of this equation. Negative 3x less than or equal to negative 9. Now I'm going to divide both sides by negative 3. And so when I divide by negative 3, got my little danger symbol there, I'm the one that chose to do that. And so in the last line, I have to change the inequality symbol from a less than or equal to a greater than or equal to. Negative 9 divided by negative is positive 3. So that's my rule. I had to apply the rule when I divided by negative 3. And I can express that answer in any of the 3 ways which I know how so far. Inequality form, graph form, or interval notation form. Here we see the closed circles and the square brackets we had talked about but didn't use earlier. But I have to apply the rule myself. The other way I can deal with this is to avoid the rule if I'm the one who caused this by dividing by a negative number. Why don't I go out of my way to never divide by a negative number? To do that, I would add 3x to both sides of this equation. Subtract 4. Oh, no, that's right. Oh, I just realized I'm not solving the same inequality that I was before because I forgot my negative sign there. Man, oh man. I knew that things were a little bit goofy. Let me back up. I need to add 4 both sides of this equation. No matter how many times I write this script before I start recording, something goes wrong. And now divide by 3. And I'm dividing by a positive number here. Everything is okay. I do not have to change the inequalities. This result is the same as before, although it looks backwards because it's written backwards. This says 3 is less than or equal to x. But I can change this around, and as long as the sign points to, big side of the sign points to x, I can do this. So if you prefer to interpret your inequalities this way with the x always on the left side, you can fix that at the end. But you see how in the end we still had to flip it. We just had to decide if we were going to learn the rule so we could apply the rule when necessary. That's what we did on the left side of the, or we would have to learn the rule so we know how to avoid the rule when necessary. That's the right side of the screen. I think they are both exactly the same. Students will tell me all the time, well, professor, it's just easier if I avoid the rule because I'll never remember when to apply the rule. I always mess up my inequality. But then you still have to learn the rule because you have to know what to avoid. And so either way, it's six of one, half dozen of the other. It gets you to the same result. And so whichever method works for you, go for it. I'm not criticizing one way or the other. That's why I showed them both to you. But I get the same result in the end. It just looks a little bit different. And I flipped around the inequality sign for a different reason. Right? One of them was the rule. The other one was, well, I'm just writing it so that I can read the X on the left side. But I get the same result either way. So that's the rule. And what I might do is after I'm done recording, I might go back in and put the shifting left and right dot for adding into the OneNote. By the way, you can look at this OneNote in the Blackboard. The link is at the top of the course content page. So you can come back and look at these notes. You don't have to copy everything I'm writing down off of my OneNote screen as I'm writing it. You can go back in and look at this afterwards. Okay, so those were linear inequalities of one variable, had an X in it and nothing else. Here's the kinds of graph you were probably expecting when I did graphing earlier. Linear inequalities of two variables. And just like when I started, I'm going to start by comparing this to linear equations of what two variables, which is here on the right side of the screen now. To make it consistent with earlier, I will change that. There we go. Yay for consistency. So graphing, for example, on the left, 2x plus y equals 10. Not too bad, right? I'll choose to graph this by finding my x-intercept and y-intercept. This method was really nice because it was fast. It didn't always work, but because this is not a strict math calculus-y kind of class, we often chose the graphs which could be solved in graph very easily using the intercepts because we don't want to use a whole lot of our time. So if I plug in x equals 0, I'm doing it kind of in my mind here, y would equal 10 because 2 times 0 plus 10, 10. And if I plugged in y equals 0, 2 times x plus 0 equals 10, would divide both sides by 2 and get 5. If that's not a skill that you have fully developed yet, please write that out. Right? Write out 2 times 0 plus y equals 10. Actually solve that. Write out 2 times x plus 0 equals 10. Solve that equation. Right? Just know that if you have the ability to do that in your head, right, it will make things faster. Right? I will never complain that you have to write that out every time. Right? I have lots of students who do. But that's one of those things that we'll be doing enough that I think is worth practicing a little bit. Let me put both of these intercept points on my graph, 0, 10. Oops, there I go, graphing it on the wrong side. Tell you what, 0, 10 is up here. And then 5, 0. As long as your graph looks roughly to scale, I won't complain too much about it. Okay. Notice here that 10 is longer than 5. Right? I wouldn't really be able to count off for it because in a graph, unless you tell me ahead of time how big the numbers should be, they don't have to be the same in both directions. It would look a little silly if you didn't, right? Because in that sense, your grid lines wouldn't be equal anymore, right? You'd have grid lines which looked like that. There's nothing wrong with grid lines which are stretched differently. As a matter of fact, we'll have to draw our graphs that way in this class. And a little bit later, like next week, we'll have to draw them that way so that they're not the same scale on each axis. But if the numbers are relatively close, it's much easier if they are equal scaled, because then your graphical visual intuition doesn't play tricks on you. I could make 10 this number and make 5 way farther out here, and it would kind of trick you into thinking that the relationship and the behavior was a little bit different, right? So I'm going to try to keep things equal on both sides, which means I've got square grid lines because they're equal on both sides whenever possible. And when I can't, I'll try to let you know. So I'm going to graph this line by connecting the two intercept points in a perfectly straight line. You saw it. So this line is 2x plus y equals 10. All the points on this line satisfy this equation, and they're all equal to 10 exactly. I didn't mark all of them specifically, but if I wanted to find some point in between, that would equal 10 if I plugged in the numbers. That's the nice part about straight lines, is that I don't need any more than 2 points to be able to describe all of the rest of them. Well, let's compare that to inequalities now, which is on the right side. I would do the same thing. I would graph my intercept points. I would find my intercept points the same way I did before. Here I'm going to be a little bit lazier. I'm just going to mark 10 and 5. Because they're on the x-axis and the y-axis respectively, I know that the other coordinate is 0. I don't need to show that every time. So we're going to mark the 2. But now before I draw in my line, I have to be careful. Remember that on the left side of my tablet, 2x plus y equals 10 was the line which connected them. All of the points which connect these two are the equals to 10. And so I don't want the equals to 10 in the inequality side of my graph. I want greater than 10. That's weird. The nice part about this is that if you were to, for example, pick points on my left side of the graph, all the points which lie on one side of the graph are greater than 10. All the points which lie on the other side of the graph are less than 10. You can't exactly tell by looking at it. It's not like a number line where the left side is always less than and the right side is always greater than. Right? When I'm looking at these graphs with 2 variables, I'm usually thinking about I need to plug a number in, or plug a whole point in. So I'm going to pick a number point which is way out here. I know this one is out here on outside of the line. I'm going to pick 5, 10. And that's just because 5, 10 is using the points from before, but together now. So if I plugged in 5, 10, x equals 5, y equals 10, that would be and put it down in my table here. 2 times 5 plus 10. Ooh, turn away. 2 times 5 plus 10. Well, that's greater than 10. And so because 5, 10 is on the greater than side when I plugged it in, that means that all the points on this side of the graph, it's hard. Well, I have to draw kind of left to right with my highlighter because otherwise it gets really skinny. All the points on this side of the graph are the greater than points. Every point that I picked in this direction would give me a number greater than 10. Likewise, if I picked a point on the other side, I can't pick a point which is on the line, remember, because the points on the line are the equal to point. If I picked a number like 0, 0, two times 0 plus 0, well, that's less than 10. And so I can see that all the points on this side of my line are less than 10. That's a really nice property of this two variable case. The line, in some sense, divides my picture into two parts. It divides it into the less than part and the greater than part. And the line between them is the equal to part. Remember, on a number line, everything is either less than, equal to, or greater than. Well, same thing in my picture. Right? All my points are on the less than side of the picture, the equal to line in between, or the greater than side of the picture. A mathematician would say the line always splits the picture directly in half. I know it doesn't look like it, but because the picture extends infinitely in both directions, right, it's not incorrect to say this line splits the infinite in half. And there's always a less than side, there's always a greater than side, and there's always a line in between them, which splits it in half. So let's see. How am I going to show that I want the greater than side, but not the line in between them? I need to show where the line is because I need to know where the boundary is. Do you remember when we started with inequalities? I had to mark the boundary. I believe that was 2, but I had to mark the boundary to show you where to stop shading. That's what the open circle was all about. I was marking that boundary. Even though I didn't want that boundary, I needed to mark the boundary. Same thing here in two variables. I need to mark this boundary. I will mark it with a dashed line. The dashed line is like the open circle of two variables. Yeah, I wrote on top of my face a little bit. That's okay. So the dashed line is like an open circle boundary. I need to know where that boundary is. And now I've already decided which side of my picture was the greater than side. So I'm going to shade everything on the greater than side. And unlike my number line, I'm not really able to put this in a more convenient form. I kind of wish I could, but everything on this side of my dashed line boundary is a solution, right? 5, 10. Right? We saw that one because we plugged it in, but I could go forever. 5, 11, 5, 12, 5, 13, infinitely many solutions in that. Likewise, I could change the x value. I could start at 5, 10, and I could go 6 comma 10, 7 comma 10, 8 comma 10, and go in that direction infinite. So in some sense, there's infinite numbers of solutions here, right? With a 2-variable case, it's more than a number line. In this weird kind of technical way, I've got lots of solutions here, and I have to show them in this way with a graph. I can't really put that in an inequality form other than the form I already had, right? This form is the inequality form of the solution, right? The whole reason we're making the graph is because we want to see another form of this solution. Here's my graph. I don't have anything representing or resembling interval notation when I have 2 variables like interval notation relied on the fact that the number line could only be read left to right. I'm going to scroll back up to my interval notation here. Notice in interval notation, the number on the left was always the first one. The number on the right, or infinity, if I needed it, was always on the right. Because the number line always was read left to right, and it could only be read in one direction. Inequalities with 2 variables don't really have that same ability, so I can't draw something like interval notation for these kinds of problems. So graphing inequalities, we'll have to do this graphically, unfortunately. And that, again, that's a good skill to practice. Being able to quickly draw a linear inequality, right, will be very useful for the next 2 weeks. I can't say it's going to be the most important skill of all of your life. Right? I can't say it will make you the next Facebook or Amazon, but it will help us understand the tools which are coming. Right? That's sort of the bad thing about classes like this one. We have to spend a lot of time building our tools, right? And those are never fun, right? Nobody likes to watch somebody build a saw, right? I would much rather see what you build with that saw once you have it. Well, right now we're building the saw. We're making our tool. It's going to take us about another week and a half to get something useful out of this tool, but we have to know how the tool works. Otherwise, we'll just be following a computer, right? I don't want to follow a computer. Right? I want to use a computer when we get there, so I don't have to do all the hard work by hand. But I don't want to just follow the computer. At the very least, I need to know what to ask the computer. Right? If I were to find a program to do this, right? I need to know what to ask. Same thing with these inequalities. The Desmos graphing calculator that we had last week when we were doing graphing of lines, they will deal with these things very well. I'll show you an example whenever we start dealing with systems of linear inequality. Right? These are graphing, it's just like graphing a straight line, or graphing inequality. Just like we had systems of equations which combined multiple lines together, we also have systems of linear inequalities. So I can combine multiple inequalities together. Each one creates that half plane solution. That's what we call it. We shaded half of the picture. I know it didn't look like half. We shaded half of the picture. And we've got lots of different inequalities. I know I could start with 2, but you know me, right? I like to jump straight into the deep end because if you can do the hard ones, you can do the easy ones. Right? To practice some of these, right, on your own. Right? I know some students will say, Professor, why do you always start with the hard one? I need the easy ones first. Well, take this hard one and remove some pieces from it, right? You see I've got 5 inequalities lined up here with 5 different colors ready to go, right? Just do the first 2, right? Or do the first one and the third one. Right? You can pick any 2 of them and do that first and check your answer because I'm going to show you how to use the Desmos online graphing calculator to check your answer. And so make your own easy problems out of the harder problems. change the numbers a little bit. The computer can deal with the changed numbers. One hard problem can be the basis for 15 easy problems. So I would rather do one hard problem with you so you can come back and see me work the harder problem than making you watch a 3-hour-long video of me doing easy problem after easy problem after easy problem, and you going, okay, get it, I get it. Do you really have to do this 5 times? Right? For you, maybe I do, right? And that's not a bad thing. Maybe you need to see it 5 times. But I'd rather do the hard way and the hard problem one time, and so you can come back and look over it. It'd be like Indiana Jones. You can take apart how this works, right? Use your little chisel and say, oh, that's why he did it that way. Or, oh, I see. So when he said this, what he meant in this harder problem, now that I'm seeing it put to use, what he really meant was something else. Right? So you can kind of get in here and dig through it. That's one of the reasons why video is so great, and one of the reasons why having that replay will be super useful. I'm going to jump straight into the quote-unquote hard problem. Here, this system of inequalities has 5 inequalities in it. And the solution, remember when we did systems of equations, the solution worked for all of the lines in the system at the same time. We did 2, maybe 3 lines in our linear systems with Gauss-Jordan elimination. I think there were some problems with 3 on the homework. We'll very quickly get into more than that for inequality. Let me say, so I want a region it will have to be a graphical region now. The solution region is part of the solution for all 5 inequalities. So you might say that I'm looking for the intersection, all 5 inequality graphs. Right. You might, if you've taken a logic class before, you might recognize that I'm looking for the and to connect all these together with an and connecting word. I'm looking for something in the region which solves the first inequality and the second inequality and the third and the fourth and the fifth, all at the same time. So how am I going to find that all 5 at the same time? Because if I have to draw 5 regions and 5 different shaded parts of this graph, I'm going to have a really bad time really fast. I'm going to start by putting all the lines on the graph. Right, remember, even if it has to be a dashed line, I always needed the line on the graph. I'm going to start with my XY chart for my intersection. I'm going to try to keep this relatively color-coded. On the black inequality, which is the first inequality, if I plug in x equals 0, that gives me 5 times y equals 45. 5 times 9, what I'm looking at. If I plug in y equals 0, see how I can kind of ignore the 5y term completely? I'm only looking at the x part. 3 times x equals 45. 3 times 15. Those are the 2 x-intercept and y-intercept for the black inequality. We're going to do the same trick for the red, same trick for the green. Oops. When I get down to the last 2, I'm not going to be able to use this trick, and I'll show you why when we get there. On the red inequality line, the second one. In the red inequality line, when x equals 0, I have negative 4y equals 8. Divide both sides by negative 4 to get negative 2. Oh, professor, you divided by a negative number. Don't you have to change the sign when you do that? Not here. Remember, I'm putting the equal sign line on the graph. Right? The equal sign line doesn't care about left side, right side. Right? I'll come back and figure out left side, right side a little bit later. I know that one of the two sides is going to be shaded, the other one is not. But when I'm putting lines on a graph, I don't care about that just yet. And I'm going to come back later and find my specific point. So I know earlier I said we change things, we have to keep track of that. But the nice part about this is that for now I'm treating these like an equation, not an inequality. The line is the equation part. If I plug in y equals 0, then 2x equals 8, divide by 2, I get x equals 4. It's really nice being able to treat these like equations, isn't it? Now I'll do the third one, the third inequality here. If I plug in x equals 0, then y equals 4. If I plug in y equals 0, then x equals. Ah! So now I've got 3 sets of inequality. And I like seeing all of them in one place because it looks like the highest number I have to go out in the y direction is positive 9 here. But I do have to go into the negatives a little bit, negative 2. So I'll keep that in mind when I'm drawing my graph. The highest number I have to go in the x direction is 15. And I know what you're thinking, Professor, your graph looks a little weird because you kind of left the negative side off of your picture. I kind of did. If you look at the 4th inequality and the 5th inequality, you'll see that I only want x values which are greater than 0, not negative ones. And I only want y values which are greater than 0, not negative ones. And so the x equals 0 and y equals 0, they were special lines. Do you remember when we talked about vertical lines and horizontal lines last week? The x equals 0 line is the y-axis. Everywhere along this line, x equals 0. I know it seems kind of weird to say the x-axis is where y equals 0, and y equals 0. X equals 0 is the y-axis. Y equals 0 is the x-axis, because the x-axis connects all the points together where y equals 0, vice versa. So yeah, it feels a little bit backwards. So these two lines, they don't need intercepts because they are the axes. Most of the time, I won't even bother to draw them. Right? I will just take them for granted as part of my picture. I will just say, oh, the x and y axes, that takes care of the x greater than 0, y greater than 0. So these lines are already on the graph. They're just part of the graph. They're the axes. Now, I'm going to mark all the way out to x equals 15. And I also need x equals 4. And so I'm going to put 4 about right here. Again, without a piece of graph paper, I can't be too specific here. 4 is closer to 0 than it is to 15. Right? Realistically, 4 should be a little bit closer to 0 than what I've drawn it. But that's okay. As long as all the pieces kind of are in roughly the right direction, you won't go too wrong. Although sometimes you will. So if you have a piece of graph paper, it never hurts to use a piece of graph paper. Right? If I were a little bit smarter, I would have actually changed my page to graph paper before I started this. But I always forget to do that. I'm going to use a computer to help you see this anyway. The computer will have a sheet of graph paper on it. Let's see, I need to mark in the y direction 9. I'm going to try to make 9 roughly where it would be on the x-axis if I were to mark square grid lines, roughly. And I'm going to put -2 out here. These are all the relevant points I need to mark. So let me connect them together. The black line connects 0, 9 with 15, 0. Those points are so far away, I will use my ruler. The ruler's not perfect, right? Because in OneNote, the ruler snaps to every degree mark. You see it changing degrees as I rotate it. It can't do half degrees. So it has to be slightly off, but it's a lot better than I could have freehanded that line. The red line connects 0, -2 with 4, 0. The closer your points are together, right, the more you'll notice this degree error if you use OneNote. The straightness of the line is more important than the exactness of the intercepts, is what I always say. That's why when I draw my intercepts, you see how I draw a really big dot? So it kind of hides the imperfection a little bit. My green line connects the points 0, 4. Oh, I didn't mark 0, 4. 0, 4 would be about right there. A little bit less than halfway. Connects the point 0, 4 to the point 4, 0. And it's okay to reuse your points. One last time with my ruler. Right? Let's see, if I would have drawn my graph correctly, this should have been 45 degrees. Did I draw it correctly? No. Does that matter? Not really. That's the nice part about this, is that as long as you mark where everything is supposed to go, then you're fine, right? Because I'm going to follow your direction. I'm grading your page. You were the one which created your graph. As long as you tell me how your graph is supposed to look and what it means when I'm looking at it, I'm okay with it being not to scale. So my grid lines wouldn't be perfect squares here, but that's okay. I've got all 3 of my lines graphed, as well as the 2 that were the axes. Remember, so technically all 5 of my lines are graphed. Ooh. Now, here's the tricky part. Remember, we're shading an entire side of the picture. So relative to the black line, everything on one side or everything on the other side is part of that solution. But the same could be said about all 5 of my inequality. To make this work, right, because this shading is going to get really tricky really quickly, here's what I'm going to do. I'm going to recognize that all of my lines have broken my graph into sections. I'm not going to bother writing the negative sections and numbering them, because notice how these last 2, y is greater than 0, x is greater than 0, I know that all of the negative numbers are not part of my final solution. They're not part of the and intersection. So I'm not going to bother with those. But for all of the other ones, and the numbering doesn't matter, I'm just numbering them for convenience. I have 5 regions in the positive part of my graph. And for each of those 5 regions, they are either part of the solution or not part of the solution. To figure out which is which, right, I need to use some test points to help me out here. And because I've got lots of different testing points, right, I'm going to try to use something which is right? Always on one side of the line or the other. 0, 0 is going to be my best friend here. Because 0, 0 is always going to live on one side of the line or the other, I can kind of use that as the universal test point to see if this works. Let me show you what I mean. Starting in region number 1. Is region number 1, is the origin part of region number 1? Yes. Well, it's kind of on that side of the line anyway, right? So let's see. Region number 1 is towards the origin from the green line. It's towards the origin from the black line. It's towards the origin. I know it seems weird to draw it that way because it's a little bit negative there. It's towards the origin from the red line. So let me ask, should the origin be shaded for all of these, the green line, the red line, and the black line? That would tell me if that is true or not true, right? Another way you could do this, if you don't like this graphical lines, origin, shadingness of it, plug in 0, 0 into all 5 of your inequalities. Well, yeah, all 5 of the inequalities. Right? I would normally tell you you can't pick a point which is on any of the lines, but the origin is on the blue line and the gray line. They are kind of special, right? Because I'm allowed to have x equals 0 and y equals 0. But the rest of them, I'll try to pick a point which is not on any of those lines. And so if you like the more numerical, algebraic, just plug in 0, 0 everywhere. I'm kind of going to do that now, even though I'm talking graphically. So looking at the green line, 0 plus 0 is greater than 4. To show you what I plugged in. I plugged in 0 and 0. Is that true or false? It's false. 0 is greater than 4? No. That's false. You only need one false to eliminate one of the regions from the graph completely. That's not part of my solution because it doesn't match with the green line. It's on the wrong side of the green line. Right? If it was on the correct side, then I would move on to a different. And remember, it has to solve all 3. Let me test region 2. Show you. So for region 2, I'm going to use let's see. So we know that as far as the green line is concerned, I should be shading away from the origin because the origin didn't work. How about the black line? If I plug the origin into the black line, does that work? That's 3 times 0 plus 5 times 0. Is that less than 45? Oh, that's true. The black line is shaded towards the origin. About the red line. The red line, you see how I'm using the red line equation? 2 times 0 minus 4 times 0 less than or equal to 8. True. So the origin, I'm shading towards the origin. So I know it feels wrong, but that's this side of the red line. Of course, when it comes to greater than 0 automatically tell me which direction to shade for the blue line and the gray line. Okay. Putting all these arrows on the graph might feel wrong at first, but I think it's the fastest way to do this. be honest with you. I probably should have done this before I even checked region 1. Because now that I've got all the arrows on my graph, where do all the arrows point? They don't point to region 3, right? Because the black arrow doesn't point towards region 3. As long as any of the arrows don't point to that region, you can eliminate it. They don't point towards region 4 because the red arrow does not point towards region 4. They don't point towards region 5 because the red arrow does not point towards region 5. That leaves only one region which remains. Let me double check. Right? Does the black arrow point to region 2? Yes. Right here. Does the red arrow point towards region 2? Yeah, it does. I'm going to look tonight to see if I can get like quote unquote a laser pointer for my OneNote. Because when I hold my pen down towards the screen, a little spider shows up, which I can move around, but you can't see that little spider. Only I can see it. So the red arrow points towards region 2. I'll use the lasso as kind of a poor man's laser pointer today. Does the green arrow point towards region 2? Yeah, it does. The blue arrow? I think so, right? I'll start here and show the arrow here. Green arrow points, or the blue arrow points towards region 2. And the gray arrow points towards region 2 as well. I know I drew the gray arrow out here, but you can think of those lines the arrows are on the same side of the line everywhere. I just drew them there because it was convenient and it didn't clutter up my picture too much. The region number 2 is the only region which all 5 of the arrows point to, which means that region number 2 is my solution region. I'm not going to be too OCD about this. I will be a little bit OCD. There we go. Now that the boundaries, it's easier to shade in the boundaries. Once you've got the, I always say the kindergarten colors will feel my pain, right? Anyone that colored inside the lines very strictly when they were a little kid will feel my pain. But region 2 is my shaded region solution. All 5 arrows point there. So that's how I know it's my solution. Remember, the solution region is the point where all 5 of the inequalities were true. And I drew my arrows to the point where all 5 were true. That's kind of a neat way to look at this. Let me show you what that would look like on Desmos. Because Desmos will do this much faster than I did. Okay, I'm going to apologize, flipping back and forth. So I need 3x plus 5y less than 45. Let me do this even better. Oops. Full screen, please. See the entire. Haha. Now I'm dual screening like a pro. 3x plus 5y less than or equal to 45. Notice how Desmos applies the shading for me. That's nice. I'm going to tell Desmos to match my colors from OneNote if it can. 2x minus 4y less than or equal to 8. That was my red inequality in OneNote. X plus y greater than or equal to 4 That was my green inequality. X is greater than 0 or equal to 0. Oh, come on. Greater than, equal to 0. That was my blue inequality. And Desmos, I believe, does not have a gray color to shade with. I will substitute it in for purple. Okay. Now let me go back to Desmos proper. Now that is a nasty, nasty mess. Even if I scrolled my graph a little bit and told it to make it a little cleaner to look at for projector mode, that's still a nasty, nasty mess. You might be able to decipher where everything is quote unquote pointing, but if I hide all of my inequalities and shading, you can see the method to my madness. Remember in OneNote when I said that we drew our arrows, we drew the arrows for each one of the 5 lines. Well, here is line number 1. And you can see instead of the arrow, right, Desmos is shading in that direction. So my shading was taken care of by the arrow. And that would made it much simpler to look at. So for the red line, you see it's the same line, but my arrow was pointing up towards the origin. And the red shading in Desmos is that side of the picture. Right? So I'm basically doing my shading with the arrows. And same thing for the green line, shading away from the origin. Right? Usually that's what I'll say. It's shading towards the origin, which is 0, 0, or away from the origin. I will never say left, right, up, or down if I have a choice. I will always say towards the origin or away from the origin. These two kind of feel like gimmies, right? Because they're the positive x values and the positive y values. So even if I leave off those two, can you see the shaded region? If I overlap all 3 of them, just the positive? Kind of, right? It's this, the colors when they get mixed together on Desmos, they look really weird. My pointer is now in the green region from OneNote. It's got all 5 points here. Here we go. So we marked all, well, we didn't mark 10,3 in OneNote. We didn't find it. But we did mark at least all these other points in OneNote. And we were able to find pretty much all the rest of them. That's maybe a little bit better, right? But I think we can do even better than that. Let me show you, this is what I'll call region 2, or method 2. Let me show you another way I can do this in Desmos. So rather than shade the regions which I want, which is exactly what I did in OneNote, rather than shade what I want, let me shade what I don't want. Right? And then instead of, in the end, picking out the region which is 5 times shaded over, I'll pick the region which is not shaded over ever. Here's how I shade what I don't want. Remember when the picture, I shade 1/2 is the greater than, 1/2 is the less than? I want the less than, so let me shade the greater than. That's me shading what I don't want. On line number 2, I want the less than, so let me shade the greater than. That's what I don't want. For line number 3, I want the greater than, so let me shade the less than. I want the greater than, so I'll shade the less than. You see how this is like reverse psychology. I'm shading what I don't want. Now, rather than see the big nasty shaded over 5 times part of my regions, is it easier to see the part of my graph which is not shaded? I think so. Easier to see the blank white graph paper underneath as the only region which is not shaded. You can think about that as the region which is not eliminated. All the other regions around this which have color in them have been eliminated. They're the wrong direction from one or more of the line. So that's another way that we can do this, I think, more quickly in Desmos. I'll see if I can dig out, because I made a worksheet for my in-person classes on how to do this sort of backwards shading in Desmos. I'll see if I can post that in my Open Math this week as something we can turn in. That'll probably be a paper assignment. I try not to do a lot of paper assignments. You might be able to just print out your graph from Desmos, because you can print out Desmos graphs or export them. Let's see if I remember how to do this correctly. Yeah, so I can print my Desmos graph or export the image. You can just upload a couple of images rather than printing it out and shading it on the paper. You can print your Desmos graph. This is really nice, right? Again, notice how I'm using my computer tools to do this faster, right? Which means that this is just a tool, right? We're building our saw right now. We're going to use these tools later this week and next week to do something better, which the computer can't really do that well, right? So use the computer to do what it can, right? And use your understanding of the process. We did it by hand, and you can do it by hand if you need to. Certainly on my Open Math, you'll probably need to do some of these by hand. I encourage you to. But we'll use the technology to help us out. That's what we call a linear system of inequalities. That's about the hardest one I could think of, 5. We'll have harder problems, but by that point, we'll have better computer methods and better methods to deal with them. That was a nice way to close out our day with Desmos. All right, I apologize. This video is a little bit longer than usual, but thanks for sticking around. And I'll try to post another video either later today or tomorrow about the maximization minimization problem. Have a good one.